Hey Hawks, this is Mr. Moog. I have a lesson for you today on the 4.3 materials from the Learn from Home lessons. We are looking at exponential growth and decay. I will take you through the notes, so I have a blank copy in front of me. So if you are taking notes on your own or you have the copy printed out, you are welcome to follow along with me. I have the exact notes we're looking at from 4.3 for Algebra 2. So I'm going to start with exponential growth. So I'm going to do all of those notes and talk about those problems, and then I'll come back to exponential decay. They are pretty much the same thing. There's just one big difference that you'll see when we talk about decay in comparison to growth. You might have already been able to guess as growth gets bigger, decay gets smaller, as those two words are talking about. So first thing is this definition. It's on the notes provided for you. I just wanted to talk through it, make some sense of it, and then we'll get into the equations and get going with some actual problems. So exponential growth is defined as a quantity that is increasing by the same amount, or the notes actually say percent, in each unit of time. So what that is actually saying is we're always increasing. So you can make a note of that if you'd like, is we're always increasing. It's never decreasing. It's always going up for exponential growth. And then the important thing is this same is meaning the rate at which we grow is always the same. So you can talk about growth rate being the same. So that's an important part of exponential growth there. The one thing that's going to change throughout all of our equations is this time piece. Time is the one changing thing. So if we look at our equation for exponential growth, we have actually all of those pieces in there and one other new piece or one other additional piece to help us talk about that. So we have the equation y equals c times 1 plus r to the t. So R is what I was talking about with that growth rate. So you can see that down here, R is growth rate. But 1 plus R is talking about the growth factor. So the reason they're different is the growth rate is telling you how much or what percentage you're increasing each time. But in order to actually increase, you need 100% of the original. You need all of it. And then you also need to add to it that plus, that's a plus right there, the growth. You can't grow if you're not starting with the original 100% and then adding growth to it. So that's why we're adding here, that plus right there is telling us that we are actually growing. And that's an important distinction there. The t, the time period here, is actually the exponent. So it's at the end of the parentheses, raised up as an exponent. And then the one other piece that's new that wasn't mentioned in the definition is this C. So C is just talking about the initial amount. So some things that C could be are the initial deposit. It could also be the first year population. C could be a lot of things, but it's all thinking about what was it at the beginning? What did we have at the very beginning of all of this growth? So once again, T is the only thing that's really going to change. So once we plug in R and once we plug in C, those are permanent. Those are part of the equation for the rest of the time. T could change. We could be asked to figure out information throughout several years. So now that we've broken down the definition, looked at the equation, all we're going to do now is read a problem or two problems and apply these formulas. So starting with example 1, we have compound interest. So it says you deposit $450 in an account that pays 2.5% annual interest compounded yearly. What is the account balance after 10 years? And you can also see there's a little hint over here, and it says the growth rate should always be written as a decimal, not a percent. So that hint box makes me realize that I actually skipped one part of our box up here for the formula, and I'm going to do this in blue so that I can make it distinct. is this percent of increase is 100R. So I'm going to put a box around this because it's a separate equation. What it's telling us is if we were given a percent or we want to find a percent that we are increasing, all we really have to do is take the rate, R, and multiply it by 100. If we want to go from percent to R, then we just flip it. We take the percent of increase, divide it by 100, and that'll give us the R. So we always want to use a decimal per this hint right here when we're working in our equation. So we never, ever want to keep it as a percent. So if we look back at our question, the compound interest is talking about a 2.5% interest. So what we need to do if we're going to talk about growth rate, or R, is we need to convert that into a decimal and not a percent. So what we need to do is take the percent and divide it by 100, 2.5%, or 2.5 divided by 100, that's just going to be 0.025. You can put 0.025 if you like, but it's 0.025. So we always are working in decimals when we go to our equation. The other part, the initial value, that's where we're talking about that number that we plugged in, the deposit at the very beginning. That was $450. So now we've found R, we've found C. The one other thing that we have to figure out, and it's not listed here, is what is this 10 talking about? It says 10 years. Years is a measurement of time. So really, we're going to say T equals 10. So maybe we'll use that in a bit. First thing we need to do is plug in the things that will never change, which are C. Our initial amount is 450. And our R is 0.025. Our equation will never ever change those. But as mentioned, we had T equals 10. That is actually also going to get plugged in. So because they asked the specific question, what is the account after 10 years? They want a specific number. So they don't want a general equation, they want a specific number here. So plug in that 10 to the exponent, and now you're just crunching those numbers. When it says simplify, you can simplify it, or you can just use your calculator. So 450, I can't do anything with yet. 1 plus 0.025 is 1.025, and that's still to the power of 10. This is where I would pull out my calculator, and I would type in 450 times 1.025 to the 10th, and there you go. There's the answer that you would get of 576.03. I'll stop at 8. So if you are working on exponential growth and you don't have a nice fancy calculator like I do, just go ahead and use Desmos. Desmos can do the same calculations for you. The final thing is asking you to interpret what this means. So the balance after 10 years will be the about. It's really just your final answer, 576.04. You can go ahead and round up to the nearest penny, so 0.04, so 4 cents. And there you go. All you're really doing is plugging numbers into a formula. So let's go ahead and go to the next exponential growth question, which is example 2. Example 2 is talking about population this time, so let's go ahead and read it. It does have 2 parts, so we're going to do both parts. It says a population of 25 mice doubles each year for 4 years. So the interesting thing in reading that is I see C, so I have my initial number of 25 mice, and I see the amount of time. I'm just going to go ahead and label that T, but I don't see R. Well, if we look, that's what question A is asking us about. It says, what is the percent of increase each year? They're asking us for that growth rate, or the percent of growth. So that's where we have to know some vocab here. This word doubles is telling you how much it's growing. We can actually do this problem without actually using equations. I'm just going to do it on the side over here. So year, we'll call it 0, when no years have passed, we have 25 mice. Year 1, we're doubling that. So instead of 25, we have double 25, which would be 50. Year 2, we'd have double 50, so we'd have 100 mice. Year 3, we'd have double 100 mice, so that's 200. And then year 4, the last year they told us would work for, we double 200 and we get 400 mice. So honestly, we just answered the question there. At least part B, it says what is the population after 4 years? 400 mice. But we're going to use the formulas and prove it. But we didn't actually answer part A, the percent of increase each year. So what we actually need to think about is what doubling with this equation actually means. So if you look at the answer for part A that's already on your paper, I'll write some other things as well. But if you look, it says the population doubles each year, so the growth factor is 2. So that's what they have written right here. 1 plus r equals 2. So that 1 plus r piece, that's the growth factor always, and that's equal to 2. What we actually want is r, and then we also want it in the form of a percent. So we want to find r, and we want to make r into a percent. So all we have to do here is solve for r. If we subtract 1 from both sides, we get r equals 1. But really, they wanted a percent. So instead of saying r equals 1, we need to turn 1 into a percent. And if you don't have a decimal, then 1 is just 100%. So really, we're going to increase 100% every year. And if you think about that, saying doubles and increasing 100% each year makes sense, because what we're doing is we're taking 100% and we're adding another 100% to it. So that's the idea of doubling, is 100% plus another 100%. That's how you're doubling it. So you're doubling the 100%, and so that's why there are two 100% there. And you can see that answer right here. So the growth rate is 1, and the percent of the increase each year is 100%. So now we've answered the first part. We've already kind of answered part B, but let's actually do the formula to answer part B here. So after 4 years, the population can be found as follows. We're going to use the same formula. You'll notice that they changed y into p. That's just talking about population. And it says c, which is our initial value. We've already labeled that up above. C is 25 times 1 plus, we've just determined that r is 1. So 1 plus 1 to the t is 4. From there, we're just going to crunch some numbers. 25 times 2 to the 4. 2 to the 4th, that is 16. So 16 times 25 gives you 400. So after 4 years, there'll be about 400 mice. So using the formula does the exact same thing as just finding each year of this experiment. And so from there, you can see how doubling works and how a formula that works for exponential growth doesn't necessarily mean that we have to do complicated math. You could see over here that it was simple math, and really we're just being able to interpret it and use the understanding of what exponential growth actually means there. So, like I said, I'd talk through the exponential growth, and then we'll talk through the exponential decay. So now let's take a moment and go through the exponential decay part of this. Like I said, they're linked. And so you can see that the definition is pretty much the same for exponential decay. A quantity that is decreasing by the same amount or percent in each unit of time. So decay and growth, the only difference is that decay is always decreasing. So if you go from year 1 or month 1 or day 1 to day 2, you're going to go down in numbers. That's what decay or decreasing really means there. And this makes sense if you look at the formula here. Everything's the exact same. So C is your initial amount, T is the time, but inside of our parentheses, our growth factor has now changed into, instead of 1 plus r, 1 minus r. So instead of saying a growth factor, we call it a decay factor. The way I differentiate between these two is growth is adding in my mind. You're getting bigger, you're growing. And decay, or decreasing, is subtracting. So decay comes from that subtraction in your decay factor there. There's another note in here that says to assure that we are within the right bounds. That's what inequalities do, is they give us bounds, tops and bottoms, things that we stay within. It's necessary that 0 is less than r is less than 1. That's really just saying once you get negative, we're not really decaying, we're doing different things. And once you get above 1, so below 0 is negative, above 1, that really changes it into a growth again. So we're restricting our r to be a certain size here. The other part here, this is not, once again, a separate statement. It's not related to that equation, but it is telling you that the percent of decrease is similarly 100r. So if you have a percent or you need a percent, just multiply your r by 100, or vice versa, go and divide your percent by 100 to find your r, just like before. So there's our equation. Let's actually do some problems. So example 3 is the only decay problem that we have, but there are 2 parts to it. So we're going to do both of those parts on example 3. So depreciation. Depreciation is the same thing as decay, and they even define it for us here. So the value of the car will be less each year because of depreciation. So that's the definition of depreciation. So the whole statement is a car is purchased for $20,000. I'm going to skip that definition. The car depreciates, loses value, once again is the definition, at the rate of 25% per year. Write an exponential decay model to represent this situation. So the first question they want us to do is just to write an equation with C and R plugged in. So all we need to do is find C and R. So the initial value C is how much money the car was worth at the very beginning. So $20,000. Then the decay rate, R, is a decimal. So we have a percent, so we need to turn that into a decimal. So 0.25 would be the decimal version of 25%. 0.25 really, a quarter. Then they want us to use Y as the value of the car in dollars, and T is the age of the car in years. So T and Y are going to exist in our equation. They're not going to be changed in our equation. And you notice that everything that was taken out is just the C, the R, those portions there. So let's go ahead and plug in C and R and get our general equation. So when they talk about a decay model, they just want a general equation. So plug in C, you get 20,000. Plug in R, you get, I'm going to do 0.25 this time, it says 0.25. And then T and Y don't change. Now we just combine 1 minus 0.25 and we get 0.75. And I'm honestly not going to change 20,000. So it's 20,000 times 0.75 to the T. So we're going to plug in any T value we want into that equation and find the value of the car that many years after purchasing the car. So there's part 1. We did it. So you can rewrite your answer on this line right here. And that equation will work for any year that that car has been purchased after. The second part of the question is to find the value in 5 years, substitute 5 for T. So they also want us to find how much the car will cost after, or be worth after 5 years. So using our general equation, 20,000 times 0.75 to the T, wherever we have T, we're going to substitute 5 for T. So 20,000 times 0.75 to the 5. Well, this is one that I would absolutely use a calculator for. Your sheet even says that. So 20,000 times 0.75. And once again, if you have Desmos, it can do the exact same thing that I'm doing now. And you get 4,746.093. I'll just go ahead and write the 3 decimal places. 4746.09. I'll put 4 since it ended with 375. And so According to the model, the value of the car in 5 years will be about, so we can just round to the nearest penny once again, 4,746, and I'll make it 10 cents, just to make my car worth a little bit more. So you can see, if we compare 20,000 and 4,746 and 10 cents, the value of the car has gone down over time. That's the idea of decay or depreciation.